In this video, we are going to look at carbohydrates for a general organic and biological chemistry audience, so an introductory chemistry class. Okay, so we can see over here an opening slide, and I am using the Flatworld textbook, so I'm using the slide, so I should probably acknowledge that. And I'll be annotating some extra information that I think should be added as well. Okay, so definitely, it's important in a GOB class to know the definition of a carbohydrate. We can see here, see if I can get my pen working. Let's see. So carbon, hydrogen, oxygen. So not a hydrocarbon that we've seen before. My students will know that word. But definitely an accessorized hydrocarbon, an accentuated hydrocarbon with oxygen. We can see here that they have functional group motifs, aldehyde and ketone. So an aldehyde essentially is RCH, where remember R just means carbon plus anything else that I'm not really interested in right now. We can put the lone pair of electrons on oxygen. I'll often won't, but just remember that they're there. So we have this important feature here for the aldehyde functional group, and a ketone functional group over here is similar to an aldehyde. It has R double bond to oxygen, but instead of an H, it has an R again. Now the R's can be the same or they can be different. If they were different, I would call one of them prime. But again, we have essentially a carbon double bonded to oxygen sandwiched between a carbon and a hydrogen in the case of an aldehyde, and sandwiched between a carbon and another carbon in the case of a ketone. So let's have a look. Okay, so that's pretty much all we wanted to point out about this slide. At least this is all I want my students to know. So we've been exposed to what a carbohydrate is. It's a source of energy. It contains carbons, hydrogens, and oxygens. I'm trying not to say the word sugar because that would be to jump to the next slide. But anyway, so let's move on to the next slide where we can actually see a chemical structure. Okay. So carbohydrates and their functional groups. In the previous slide, I guess I jumped into it. I couldn't help it. We looked at the functional groups. So we can see this functional group here. So remember I said it was for the aldehyde, it's R, C, double bond, O, put the lone pair in if you like, H. Now this R, remember it means carbon plus other stuff. Look at this bond here. It's carbon plus other stuff. So this entire structure here, this is the beauty of an organic chemist's abbreviation R. All of this is R. And if you changed it, you could still call it R. The important thing about calling something R is that the bond must be directly bonded to a carbon. As long as you have a carbon, nothing else matters, you can call it R. Okay, so we clearly have our aldehyde functional group. And here we notice we have our carbon double bond, and we've got immediately a carbon here and immediately another carbon here. Now, in this case, remember we said that the ketone was R carbon double bond O, which eventually I'll give you the name of. And then R, now R can be the same or it can be different. In this case it's different. This whole structure here, let's call this R. Clearly this structure is different. So let's call this structure R prime. So we've got an R prime and an R, it doesn't matter what side you put them on, sandwiched in the C double bond O. So I don't ever have to say C double bond O again. Let me just tell you what the C double bond O is. A carbon with a double bond to oxygen, henceforth we will call it a carbonyl. So now I don't have to keep saying C double bond O. It's a carbonyl. So an aldehyde and a ketone, they both contain a carbonyl, sandwiched between an R and an H in the case of aldehyde, sandwiched between two carbons or two R's in the case of a ketone. Okay, there's not much more I want to say about that slide, so let's move on. And incidentally, I have about 23 slides here. Okay, so these are just out-the-box slides. I'm just going to annotate some of them and point out some things to my students. Okay, for the most part, well, first of all, some vocab here, right? So this word saccharide, this is the fancy chemical name for sugar. So wherever you see saccharide, you can think sugar. Mono means one. So a monosaccharide is one sugar molecule, and essentially it's the building block of more complicated sugars. So a monosaccharide is one sugar unit, and it's essentially the building block. For the most part, we'll be looking at, so we'll consider 3 and 5 carbon structures for this course. We'll mention a few others, but only just so we can be exposed to them. But we'll be looking at 3 carbon sugars and 5 carbon sugars. And they come in 2 major families. The aldoses, so this is important vocab. The aldoses and the ketoses. And you won't be too shocked to learn that the aldoses contain an aldehyde, or they're based on the aldehyde structure. And the ketoses, drum roll, are based on the ketone structure. So that's why it's definitely important to know an aldehyde when you see it, know a ketone when you see it. We should also mention that the suffix OSE is synonymous with sugar. So we've replaced "ide" and "one" with O's and O's. So you can see the suffix here, O's and O's. Think of sugars that you are familiar with, glucose and fructose and lactose. So these are all sugars that you're probably familiar with from your diet or inspection of nutrition labels. So anything for the most part that ends in OSE, odds are it's a sugar or a monosaccharide or a polysaccharide. Okay, So we're looking at some vocab here. We're looking at types of monosaccharide. So let's see. Yeah, we should probably detour a little bit and talk about chirality. Chirality can become a complicated topic, but at this level in a GOB class, we'll keep it real simple. So let's see what they say, and then we might annotate a little bit on top of it. I like what they say. We'll see if they give a diagram. In fact, I'll probably just doodle a diagram anyway. So we're going to see a chiral carbon in this course is going to be a carbon atom that has 4 different groups. Okay. What does that look like? Well, essentially it's carbon. We know the carbon likes to form 4 single bonds. So let's say it's got 4 different groups. Let's call them A, B, C, D. And what's important is that A does not equal B, does not equal C, does not equal D. That's what's important. If we see that, then what we can do, we can label a chiral carbon with an asterisk, and we would call that specific carbon with the asterisk a chirality center. So I might ask my students to identify chirality centers within a structure. I might ask you to count how many chirality centers are there in a structure, or which of the following structures has 3 chirality centers. Okay, this vocab here, enantiomers, non-superimposable mirror images, I'll probably have to draw something about that. I don't think these slides will contain anything. Okay, so let's focus on these 2. We'll worry about stereoisomer. Actually, we've seen an example of a stereoisomer already in the previous chapter, organic chemistry chapter. So a stereoisomer is an isomer that has a different shape. Stereo means shape. So for now, I'll just say C cis-trans isomers. So go back in your notes and look at cis-trans isomers of alkenes. So in the previous chapter for my students, we looked at cis-trans isomers, and that would be an example of a stereoisomer. Enantiomers are also stereoisomers, but they're not cis-trans isomers. First of all, the type of stereoisomer we've seen, this cis-trans isomer, it applied to alkenes, and remember alkenes have carbon-carbon double bonds. In the case of enantiomers here, at least at this level, we're only interested in carbon single bonds. So that's one thing to keep an eye out for. I'm going to have a little detour and see what we can say about enantiomers. I just want to see if there's a picture on the next slide. I don't think there is. So why don't we just draw something real quick about non-superimposable mirror images and enantiomers. Okay, so I'm going to draw this here. So let's say we have our chirality center. So let's say we have the structure A, B, C, D. And let's say we can do a little bit better than that. We can actually write a line wedge diagram. So let's do this with some kind of attention to what it really looks like. So remember, going counterclockwise. We have line, line, wedge, and dash, and let's put B, A, D, C. In this occasion, the central C here is carbon. This C is just the letter C. So maybe I shouldn't have picked C, but there you go. Let's say we have a mirror image, or a mirror here. So let this be a mirror. Let's draw the mirror image. So we would have, let's see, we'd have carbon. We'd definitely have the B going straight up. We'd have the A coming out. And then we'd have the wedge going towards the mirror, or at least the reflection of the wedge. D. So that would be a mirror image. So what we now have are two chemicals that are mirror images. We have a pair of enantiomers, or some people like to say an enantiomeric pair. Why are they non-superimposed? Well, first of all, they're mirror images, check, but they're also non-superimposable mirror images. So non-super impose. Let me get rid of that. Imposeable mirror images. So they have to be mirror images, but they also have to be non-superimposable. How do you know the non-superimposable? Well, try it. All we can do is rotate. So you could, if you like, if I were to take this chemical on the right, and if I were to, let's see, rotate 180 degrees. So essentially that I basically flip the C and the D over. So I would have, if I start to draw it, hopefully you'll see what I mean by 180 degrees. So flip it that way 180 degrees. Then the A and the B would start to look like the original. But then I'd replace the C and the D's wedge and dash respectively. So that C that was a wedge would now, that was a dash would now become a wedge. And the D that was a wedge would now become a dash. Well, this chemical, my effort to reproduce the original, clearly if I compare that with this, they're not the same. They're not the same because here the D is a wedge and here the D is a dash. So again, it's impossible to recreate the original, so they're non-superimposable. We have an enantiomeric pair. That means these central carbons are chirality centers. Okay, so that's probably enough of an aside to make us dangerous enough to be useful. So let's go back to our next slide. Okay. So here's a new word they just snuck upon us, triose. triose, here's the plural, trioses, but what's a triose? So let's get rid of the S. Well, first of all, it's a sugar because it ends in OSE. And tri means 3, so it's 3 carbon sugar. 1, 2, 3, 1, 2, 3, 1, 2, 3. So these are all trioses because they are sugars that contain 3 carbons. But we can do a little bit better than that. And again, I might be preempting a future slide, but I don't see a future slide right now, so I'm just going to preempt away. Notice that this is an aldehyde functional group. So this is an aldotriose. It's an aldotriose. Specifically, it's a triose based on an aldehyde structure. Likewise, this is an aldehyde. So we've got another aldotriose. And here we have a ketone. So this is a ketone. The carbonyl here is sandwiched between 2 identical R groups. So this is a ketotriose. So this is extra vocab I'd like my students to be aware of. So at least for my students, not for anyone else's students, but I would never expect my students to know these names. So I'm never going to ask my students to identify these names. That wouldn't be reasonable in my opinion. But I can't speak for anyone other than myself. So my students don't need to memorize. But do know the type of monosaccharide. So I do expect you can identify whether a sugar is a ketotriose or an aldotriose or what have you, but I'm not going to ask you which of the following is glyceraldehyde. Okay, so hopefully that's clear. Okay, I think we've exhausted that slide. Moving on. Okay, this could be worthwhile knowing because there's not that many of them. But essentially some important hexoses. So this is a new vocab word, hexose. What could a hexose be? Yep, it's a sugar O's that has 6 carbons. 6 carbon sugar, or monosaccharide because it's just 1 unit. Here we've got an aldehyde group. So this is glucose, so brain food, the preferential food for our bodies, including our brains. So this is a 6 carbon sugar. It's a hexose because it's got 1, 2, 3, 4, 5, 6 carbons. But it's also an aldehyde based one, so that it's an aldohexose. Aldehyde, so is this one. So an aldohexose, galactose found in the disaccharide lactose, which is found in milk. And here we have a ketone. This is a ketone, 6 carbon still, but a ketone. So this is a ketohexose. All right, a ketohexose. Fructose is found in honey and in regular table sugar as well, but we'll get to those structures later. Okay, so again, these structures are very subtly similar. From a chemist's point of view, the names are not that important. More important is the structure. So this D, these D's, these will become important, and we'll get back to those. Essentially, these letters are going to be important, but we're not quite there yet. Okay, so I think that'll do us with this slide. Okay. Oh, I didn't mean to move the slide, I just meant to move the board. Okay, let's try and get that down. Unfortunately, when these slides import into this app I have here, they always come in pairs of 2. They don't just come in a complete column, so that's a glitch. But anyway, we'll do what we can. Maybe this slide, I'm not, to be honest, I would ignore this title because it's not really talking about that, is it? And again, I'm doing this for the benefit of my own students who have these slides available to them. Yeah, I would just say, I would call this, well, first of all, let's look at the chemistry. Okay. So I would definitely want my students to know this chemistry. I think this is important chemistry. It is related to cyclic structures, but it's odd that they don't show it on these slides. So let's have a look at the chemistry anyway. So I'm actually going to get rid of that because I think we can expand it a little bit over here. Okay. So first of all, there's types of alcohol. Types of alcohol. There's first degree or primary. There are second degree or secondary. And then there's tertiary, third degree or tertiary. Okay, so there's types of alcohol. If we look at primary alcohols, a primary alcohol just means that the carbon that contains the OH bond, this carbon, is bonded to only one other carbon. That's what makes it primary. So therefore it must have 2 hydrogens here. Okay. Now we're not really interested at this level, again, which is a GOB class, General Organic and Biological Chemistry, intended for a nursing level student or an allied health student. So we're definitely at the sub-general chemistry, sub-organic chemistry level. We're not really interested in mechanisms, we're just interested in outcomes. So primary alcohols, I think what I want my students to know is primary alcohols can be oxidized and for now oxidized just means we add oxygen. So I'm adding oxygen to give an aldehyde. Do you know what? I shouldn't have. Do you know what? I'm not going to bother with these lone pairs because once you do some of them, if you don't do all of them, it's weird. So just assume that the oxygen has its lone pairs where appropriate. So a primary alcohol can be oxidized to an aldehyde, and the other product is water. Okay, so this is an aldehyde. The aldehyde, actually let's put the, oh, let me try and erase that. I guess there's a little delay on my eraser. Not 100% sure what I'm doing now. I was trying to erase. Thought I knew how to erase, but clearly I don't. Oh, there we go. Okay. Let's put the water down here because there's a second reaction where the aldehyde can be further oxidized. Let's just say add more oxygen to give a carboxylic acid. This is a carboxylic acid. Remember, the pH is less than 7. So you could actually monitor this progression via pH. Okay, so primary alcohols can do that. So I want my chemistry students to know that. Secondary alcohols here, the carbon that contains the OH is bonded to not one but two other carbons. They can be the same, they can be different, but two other carbons and only one H can undergo oxidation. So it's oxidized to give a ketone. So the two functional groups that we've been looking at so far in this video, the aldehyde and the ketone, come from two different types of alcohol. And once you form the ketone, there's no further oxidation. So we're done with ketones here. So you could oxidize an alcohol, an unknown alcohol. If its pH drops, you've got evidence that you had a primary alcohol. If the pH doesn't really change that much, you've got evidence that you had a secondary alcohol. Okay, what about tertiary alcohols? Okay, so tertiary alcohols the carbon that contains the OH is bonded to three other carbons. They can be the same, they can be different. But when you try and oxidize them, there's no reaction. We can just write NR for no reaction. So tertiary alcohols are much more stable. They tend not to do that much So this is what I would like my GOB students to know. Okay, so with that said, let's get back to what the slide was yarning on about. Okay, which I guess was subtly different. Okay, so aldehydes and alcohols. Okay. Okay, so let's add then, so now I can see. Okay, so I want you to know that. So aldehyde plus alcohol. Well, let's see. We've got our aldehyde. We've got our alcohol. Let's see. It really depends what they want to show you. Okay. So they've got the OR. Okay. Okay, so again, the mechanism is not really that important to us, but we'll write the alcohol like this. So remember, an alcohol is carbon with an OH stuck on it, so it has to be at least a carbon here. So I'm just saying this whole thing is R. Okay, well we know, well actually we haven't really specified this yet, have we? We said earlier that the carbonyl group was C double bond O, but we should probably say something about the carbonyl. The carbonyl is a source of attack, or is prone to attack. So the carbonyl is a polar bond. So we can annotate that with an arrow pointing in the direction of the more electronegative oxygen. Oxygen has an electronegativity of 3.5. Carbon has a value of 2.5. The difference is 1. And because 1 is greater than 0.5, it's polar. And because it's polar, we give it this annotation here. And we point our arrow in the direction of the dominant element, which is oxygen. We accessorize the oxygen with a delta negative sign. That's an accumulation of partial, delta just means partial negative charge. That's my dog barking in the background, I apologize. What a silly animal. Where we have this plus sign here on the tail of the arrow, we annotate that with a delta positive. So we have this dipole here, this polar bond. Dipole just means different ends. We have two different ends. We have a minus and a plus. So that means that the carbon has a positivity about it, and therefore any electrons can attack that carbon. Okay, so keep that in mind. So this is our little thought on the sidelines. Well, I've got oxygen here with its lone pairs. The lone pairs of that oxygen just say yummy to that carbon. Now this, I said we're not interested in mechanism, but it's just a habit at this point. Then this double bond, actually this is not exactly the mechanism it will follow, but it could be. If you don't know any better, you could definitely say it could be. We'd probably protonate the oxygen first, but it doesn't matter. This double bond can then break, and there can be an accumulation of negative charge here. Well, that negative charge can then be used to snag this hydrogen. So why don't I'll try and color code. Let's see if I can color code. Yeah, let's make this hydrogen green. and then see if I can pick my red again. Okay. So that when our oxygen attacks, we will have R. Let's call this R prime so I can tell it's not this R over here. So we'll have R, C, O. We've now got O, R prime. We've got H, and if I can get my green to behave, we've got that green H over here. So if you look at this structure, this structure is exactly what we had over here on this slide. So it's this structure over here. All right. So what would you call that? So this has something very special. This is a very special group. This is actually, let me get that full thing back. Sorry for this clunky software. Okay, so this is actually a really important group in carbohydrate chemistry. We notice we have a carbon in the center. Well, first of all, it's chiral. So that's one thing we should point out. It's chiral because I've got a carbon with 4 different things. So I should label that with an asterisk. I've got a chirality center. R is different than OR, is different than H, is different than OH. I've got 4 different groups around a central atom. So my A and my B, my C and my D are all different. So I've got a chirality center. So I know that its mirror image won't be superimposable with it. Okay, it can form an enantiomeric pair with its mirror image. Okay, so that's one thing. But this specific molecule is a new type of functional group called a hemiacetal. Hemiacetal, 2 words. Hemi means half, so this is actually half of an acetal. So just real quick, because I'm sure acetals are coming up. Let's look at an acetal, then we'll see a hemiacetal. So a full-blown, fully formed acetal is a carbon with an O carbon, O carbon. Can be the same, can be different. And then it really doesn't matter what these are, so let's just make them carbon for argument's sake. But what's important is this bit. It's a carbon with 2 O carbons joined to it. That's an acetal. A hemiacetal is half of that. Hemiacetal is going to be a carbon with an OR and an OH. And that's the important part of a hemiacetal. So it's half because it's only got 1 OR, whereas the full acetal has 2 ORs. So whenever you see this, and we can see our carbon here with its OH and its OR, we notice it's a hemiacetal. This is going to become important when we cyclize these monosaccharides. Okay, Alright, so we are cooking. I'm definitely going to keep this video to around an hour. We're not going to get through all of these slides in an hour, so we'll probably have to do a second video. Or at least till I'm satisfied that my students will nail their assessment on carbohydrates. Okay, so I think we've now looked at that slide. Yeah, so now we can, so this is where I would have put in the cyclization bit and nowhere else. Okay, so let's look at the cyclization of monosaccharides. Here we have an aldohexose. So this is an aldohexose. 6 carbons, hex, sugar, O's, aldehyde structure, aldo. Okay. It's not really a Fisher projection, so I would beg to differ with that. So I'm going to get rid of Fisher projection there. We'll draw the Fisher projection of this right now, I guess. So essentially a Fisher projection, if I were to draw that as a Fisher projection, I would do this. Because Fisher projection acknowledges chirality centers. So this sugar and all sugars have a multiple of chirality centers. So carbon 1 is not, because I've only got 3 bonds and I need 4 bonds, so that can't be a chirality center. Carbon 6 is not, because I've got 2 hydrogens, so that's 2 of the same thing. So that's not either. But carbon 2, 3, 4, and 5, they are chirality centers. So in a Fisher projection, you draw it with this plus motif. So that's why I don't think I would label the original a Fisher projection. Because again, the Fisher projection has this motif of a plus sign. OH, H, H, OH. So this is a Fisher projection. Okay. Now, Fisher projections are linear. The acyclic. Acyclic just means not cyclic. And now we've got something that's cyclic. What's cyclic? The Haworth projection. So one thing I want my students to be able to do is to be able to go back and forth between a Fisher projection and a Haworth projection. This is one of my go-to assessment questions, so a strong nudge in the arm that this will be something you have to do. Hint, wink. And there's definitely ways that you can do it. I'll probably just go ahead and just draw something in the margin here. I'll just feel better if I do that, if that's okay. All right, so this is how I would like my students to do it. Take your Fisher, so let's just say CHO is the aldehyde. So let's draw a Fisher real quick. Doesn't matter what the sugar is. But let's keep it to an aldohexose. So CH2OH. And the important thing is that every chiral carbon has an H on one end and an OH on the other. For now, it doesn't matter where they are. So if you have an OH and an H and an OH. So for now, just make sure you have one of each. All right. So there's our sugar. It's our Fisher projection. Now, definitely a good rule of thumb is to number the carbons. Helps you keep track of the structure. And now what we're going to do, we're going to draw it in a slightly different way. Redraw, ready for cyclization. I don't know if that's a word. I'm just going to say cycle formation. I chickened out of inventing a new word, cycle formation. So here's how we're going to do it. So there's our So we've kind of curled it round. This is now carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. We've got carbon 6 up here. Okay, so it's important to keep track of your carbons. Okay, so we've got that. So I've redrawn it ready for cyclization. Now we're actually going to, we should probably put the other structures on. So, let's see, I've essentially rotated it that way, right? So essentially move this thing almost 90 degrees clockwise. So it's almost 90 degrees clockwise. Okay. So what does that mean? That means right becomes bottom and left becomes top. That's what that means. So if I've got on carbon 2, I've got a hydrogen on the right. When it tilts 90 degrees clockwise, that becomes bottom. So I have a hydrogen on the bottom. Therefore, I have an OH on the top. Carbon 3, I have a hydrogen on the bottom and an OH on the top. Carbon 4, I have an OH on the bottom and a hydrogen on the top. Okay, so I've got my hydrogens and my OHs on the right location. And now finally, I'm going to close my cycle. So I'm essentially going to have, again, this alcohol is going to attack the carbonyl. So this oxygen is going to attack that carbonyl, close in the bond. So again, I'll redraw it. So we'll say this is carbon 1, carbon 2, 3, 4, 5, 6 again. Let's put our OH up top, RH down below, OH up top, RH down below, our OH down below, and our H up top. So the location of the oxygens and the hydrogens and what have you on carbons 2 through 4, they are fixed based on this right becomes bottom. So this is carbon 2 through carbon 4. Okay. Carbon 1, the carbonyl carbon, it's over here, right? Here I've got almost like a skeletal structure. I don't represent the carbon, I just have a dot. But importantly, carbon 1, how do you know whether the hydrogen is up and the oxygen's down or vice versa? Well, you don't. You can't predict that. So this oxygen, we have to be told separately. We have to have new language because there's no way to predict it. Depends what side the original alcohol attacked from. So essentially, if it's down, we call it alpha, and if it's up, we call it beta. So if I were to have the oxygen up here, we'd call it beta, and that's what we would call it. So we would call these, well, first of all, it's a couple of things. This carbon here that I'm going to color in now, this is called the anomeric carbon. It's a chirality center. And I'll use blue. If we look at the carbon again, we've got O and then carbon. So this thing here, if you like, could be our OR group, carbon, and then I've got OH. So essentially I've got carbon, OR, OH. So I know that this whole structure contains a hemiacetal. So this is a hemiacetal. It's also, don't forget, our Haworth projection. So this is why those slides before were harking on about Haworth, about attacking aldehydes with alcohols. So let's see if I can get this board to move back. Okay. So this is how I'd like my students to be able to do it. Obviously it's reversible, you can go back again. In which case bottom would become right and top would become left, etc. So again, practice Fisher to Haworth, Haworth to Fisher. You can use this idea to figure out carbons 2 through 4. Sorry, 2 through 5. Oh no, sorry, 2 through 4. That's weird, I lost my 4 here. 2 through 4. Carbon, let's see, which carbon would that be? Carbon 6, it doesn't matter because it's just floating around up here. Carbon 5, we'll get to that in another video. But carbon 5, we have another way to mention that. And then the carbon 1, we now know is either alpha or beta. So I'm going to leave carbon, well, I'll tell you what it is. It's either going to be D or L. So it's all on one screen. I won't give you any details yet. It'll have to wait because we're at the hour now. So essentially, in this aldohexose, you've got 6 carbons. Carbon 1 will have a designation alpha or beta in the Haworth form. Carbons 2, 3, and 4, we use this conversion, right becomes bottom, left becomes top, etc. Carbon 5, we'll see soon, will have a designation D or L. And my dog's yapping away, so that will have to conclude this video, and I will set about making the second video.